Today we shall study linear congruences. First we shall see what is the meaning of linear congruence and type of the congruence. A congruence of the form Ax congruent to B modulo n is called a linear congruence. See the linearity of this variable term Ax. It is first degree term and therefore this congruence is said to be linear congruence. Now what will be solution of this linear congruence that we have to study? An integer, it is similar to linear equation or algebraic equation. A value of x which satisfies this congruence is said to be a solution of this congruence. So an integer x naught which satisfies this congruence, or it is such that Ax naught is congruent to B modulo n, then an integer x naught is such that it satisfies this congruence, then x naught is a solution of the congruence. We suppose this as 1. Now we shall consider an example. Say 3x congruent to 9 modulo 12. This is a linear congruence. What is the value of A is 3 and B is 9, n is 12. Now what is the solution for this congruence? Then we see x is equal to 3 and another we can consider also x is equal to minus 9 are solutions. Are solutions of this congruence, or we may suppose this congruence as second. Why? Because these two values satisfies the congruence. Put x is equal to 3, then it is 9. 9 is congruent to 9 under any modulus. So therefore our 12 divides 0 and this is a solution. For x is minus 9, 3 into minus 9 is minus 27 and minus 27 minus 9 is minus 36. 12 divides 36, minus 36, and therefore this is also a solution. By definition of congruences we can check. But whether these are the only solutions, that we have to see. And there are other solutions also. And to find other solutions, we may note again this congruence. Here 3 is a common factor. And also one thing is that the GCD of 3 and 12. Further, GCD of 3 and 12 is 3. And therefore we can divide both sides by 3. Also we have to divide this modulus by 3. This is theorem 3. Therefore by theorem 3 we can write 2 implies this after division by 3 it is x. X is congruent to 3 modulo 12 divided by 3 is 4. Now it becomes simple, and see the solution for this is x is equal to 3. Another solution can be considered as, so this implies, or this has solution as x is equal to 3, one solution. 3 is congruent to 3 under mod 4. Again we say 7 is solution because 4 divides 7 minus 3, that is 4 divides 4 and therefore x is equal to 7 is solution. And one more thing we can consider 11. 11 minus 3, that is 8. 4 divides 8 and therefore these are solutions. But not only these, modulo integers to these are all solutions under modulo 4 are solutions of this congruence. And these are also solutions of the second congruence because the third is obtained from the second. Now you may check 3 is solution that we have seen here. 7 is also a solution from this. 3 into 7, 21 minus 9 and 12 divides 12. Therefore, it is a solution. 11 is also a solution. 33 minus 9, 24. 12 divides 24. Therefore, these are the solutions. Now, what is the difference between these two solutions and these solutions? So, these are solutions of 3 and these are also. Therefore, this x is congruent to 3, 7 and 11. So, actually these are different. X is congruent to 3, x is congruent to 7, x is congruent to 11. But we are writing together under modulo, this original modulo 12 are solutions of 2. Actually, the original congruence is second. Third is only for simplification to get one solution. And if you get one solution, the others can be obtained here. That is obtained by adding 4, you may see. And now what is the difference between this solution and this solution? Here, these two solutions, x is equal to 3 and x is equal to minus 9, are solutions of second, but these are congruent to each other. And therefore, we say these are not different, these are the same. Now, but 3 congruent to minus 9 modulo 12, and therefore x is equal to 3 and x is equal to minus 9 are not different solutions, not different solutions of 1, solutions of 2, or these are congruent solutions of 2, or they are congruent. Congruent to each other. Congruent modulo 12. Now what about the remaining? See these 3, 7 and 11. These are not congruent to each other under modulo 12. That we may see. 3 is not congruent to 7 modulo 12, but 3 and 7 are solutions of 2. 7 is not congruent to 11, but these are also solution of 2. And further, x congruent to 3, 7, 11 modulo 12 are solutions of 2. Which are incongruent. Incongruent modulo 12. So thus we are interested in incongruent solutions. Congruent solutions are said to be not different, they are equal, and therefore we don't want this type of solution 3 and minus 9, but we consider only 3 and other are 7 and 11 modulo 12. So the existence of solution of congruence. This is our theorem 4. The linear congruence has a solution if and only if necessary and sufficient condition D divides B, if and only if D divides B, where D is GCD of A and N. That is first part. And further, if D divides B, then there are exactly D mutually incongruent solutions. Then there are mutually incongruent, D mutually incongruent solutions. So this is the theorem. The theorem states a necessary and sufficient condition for existence of solution. And second part, if that condition is satisfied, then how many solutions, incongruent solutions will be there. Now we will see the meaning of the theorem in terms of this example. Now we may compare Ax congruent to B mod n like this. 3x congruent to 9 mod 12. Here what is the value of A? A is 3 and B is 9, n is 12. Now what is the GCD of this? Say GCD of 3 and 12 is 3, and that is our value of D. And this D, clearly 3 divides this number. So D divides B. This number here is B is 9, and 3 divides 9, therefore it has a solution. How many solutions? D number of solutions. If D divides B, then it has exactly D mutually incongruent solution. And therefore here D is equal to 3, and this D divides B means 9, and the congruence second has 3 incongruent, mutually incongruent solutions. And we actually have obtained these solutions. These are 3, 7 and 11. So these are 3 mutually incongruent solutions of this second congruence. That is the meaning of this theorem. Condition is D must divide B. What is D? D is GCD of these two numbers. So that is the GCD of these two numbers must divide this number. And if it is, then the congruence has the GCD number of solutions, D number of incongruent solutions. Now the proof of the theorem. So the given congruence is, we have Ax congruent to B modulo n. Suppose this is 1. Now by definition of congruence, this implies n divides the difference of Ax and B, that is Ax minus B. And now by the definition of divisibility, this implies Ax minus B is multiple of n, or that means Ax minus B is equal to n times y, where y, for some integer y. And further, this implies, we can write, now this is an equation, and this is Ax minus ny is equal to B. Now we suppose this as second. So first implies second and second implies first, or we may write double way implication. And therefore the congruence 1 is equivalent to equation second. And we know this is a Diophantine equation. We have studied in the first chapter. Ax plus by is equal to c. Linear equation in x and y. Single equation, linear equation in x and y is Diophantine equation. And therefore the congruence 1 is equivalent to Diophantine equation second. And we know the method of solving Diophantine equation. And the Diophantine equation, theorem on Diophantine equation, we have to refer. Now that Diophantine equation has a solution if GCD of these numbers on left side, that is GCD of these two number divides B, and we have GCD of this as D. The Diophantine equation 2 has a solution if and only if. See, this D divides B, where this is referred here the theorem on Diophantine equation, where D is equal to GCD of A and N. You should refer the theorem on Diophantine equation. There is change in the notation. Actually, the Diophantine equation is C. It is AX plus BY is equal to C. And here the GCD of A and B divides C. Then that equation has solution. And the solutions are given by X is equal to X naught plus B by D. What is D here? GCD of AB. And that is B by D into T, and Y is equal to Y naught minus A by D into T. Now there is change in notation. See what is the change, you may refer here. It is AX minus NY is equal to B, and thus we have AX minus NY is equal to B, or we want here plus sign, so we may multiply by minus sign, and AX plus Ny is equal to minus B. The equation can be expressed. And what will be the solution according to this? This will give the solution as X naught plus X is equal to X naught plus, what is B here? B here is, you see this equation, N by D. The notation is the same. And for Y is equal, this is X, and Y will be Y naught. And now what is A? Instead of A here, it is minus A, and that minus and this minus becomes plus, and therefore it is plus A by D into T. So these are the solutions of this equation. This is the same as, and this has the solution. So we refer this result of Diophantine equation here. And thus the Diophantine equation 2 has solution if and only D divides B, where D is GCD of A and N. So this proves the first part of this theorem. And further, it has a solution if equation 2 has solution, if further D divides B, then 2 has a particular solution. If you consider if D divides B, then 2 has a particular solution, X naught Y naught, and any other solution, and other solutions are all solutions are given by this relation, that is X is equal to X naught plus N by D into T, and Y is equal to Y naught plus A by D into T, where T is an integer, where T is any integer, positive or negative it may be considered. So thus this is written according to the Diophantine equation theorem. Now we want to consider D solutions and show that these D solutions are incongruent. Now how to take D solutions? All solutions are given here by integer values of T, and we will consider the values of T as non-negative. For taking T is equal to 0, 1, 2 up to D minus 1. Now these are D values. We further want to show there are exactly D's incongruent solutions. We have the values of X, or that is solutions of say 1. Values of X will be solutions of 1. Or now put T is equal to 0, we get X naught, and you see we don't consider this Y. Y is not there in the linear congruence, only we require X value. Solution of this means value of X which satisfies 1. So if it is Diophantine equation, we require both values X and Y. But to get the solution of congruence 1, we require only X, and therefore we are considering only this part. And in this, we are putting the value of T from 0 to D minus 1, D values, to generate D solutions. So first is X naught, T is 0. And second is T is 1, so that is X naught plus N by D. next is x naught plus d is t is 2, and that is 2n by d, and so on. The last is x naught plus, now see, t is d minus 1, so it is d minus 1 times n divided by d, and these d solutions are there. We will refer this as 3. Now what we want to show is that these 3 solutions are incongruent, that we have to show, and we shall claim it. Now we claim that the solutions in 3 are incongruent modulo each other, incongruent to each other modulo n. So further say we claim that the solutions in 3 are incongruent modulo n. Now if not, what will happen? If not, then we will have some of the solutions will be congruent to each other, and we will write like this: x naught plus, say it is n by d into t1, one solution, and that is congruent to another x naught plus n by d into t2 modulo n, where, see, of this kind we are considering x naught plus n by d, t1 on left side, t2 on right side, and where t1 t2 has the values between 0 to d minus 1, where 0 is less than or equal to t1 is less than t2 is less than or equal to d minus 1. This is the condition. T1 t2 lie between these 0 and d minus 1. So but what this implies, so you may see, this implies x naught can be cancelled from both sides, and we get n by d into t1 is congruent to n by d into t2 under modulo n. So, and further, now you see n by d is common on both sides, and but to cancel it from both sides, we have to note the GCD of n by d and n. So we should note the GCD of, now GCD of n by d, we are referring theorem 3 of congruences, this chapter, n by d and n. Though it looks fraction, it is an integer because d divides n. So d is divisor of n, therefore this is integer, and smaller is n by d, therefore the GCD is n by d. And therefore this implies by theorem 4, by theorem 3, we have, now we can divide here both throughout by n by d. So it gives t1 is congruent to t2, n by d is divided out, t1 congruent to t2, and this n is also to be divided by this GCD n by d modulo n divided by n by d. But you see, what is this modulo? N divided by n by d, or that is, this implies t1 is congruent to t2 modulo n cancels, and 1 upon 1 by d is d. Check it. And again, by definition of congruence, this implies d divides difference of these two, or d divides the difference we shall consider t2 minus t1 or t1 minus t2, it is the same. Why t2 minus t1? Because we have assumed t2 is greater than t1, and now this is a contradiction. So why this is a contradiction? You see the inequality for t1 t2. t1 t2 both are less than d minus, less than or equal to d minus 1 means actually they are less than d, and therefore their difference is also less than d. But here d divides this t2 minus t1, a number here that is greater number divides a smaller number, d is greater than this. So this is a contradiction. This is a contradiction since by the inequality. By the inequality of T1 and T2, we have 0 is less than T2 minus T1 is less than D. Both numbers are less than D, their difference is also less than D. And thus, the number which is greater than this, greater number cannot divide smaller number. So, thus, greater number will not divide. We have 2 can divide 4, but we can't say 4 divides 2. And therefore, here this D number is greater, integer is greater, and this is smaller, and this is a contradiction. Why this contradiction has arrived? Because we have assumed not congruent. These are not congruent. These are congruent. These are congruent that we have assumed, and we get a contradiction. So therefore, what must be true? That these are not congruent. If you assume congruent, then we will get a wrong result or contradiction. So this shows that the solutions in 3 are incongruent. So our claim is the solution in 3 are incongruent. Therefore, we can say the solutions. Therefore, the solutions in 3 are incongruent modulo n. So thus this we have proved, mutually incongruent. Now the next thing is, these are the only mutually incongruent solutions. That is the word exactly. Now what about the other solutions? Their solutions can be written infinitely many, but the other solutions will be congruent to one of these. Then there will be exactly D number of incongruent solutions. That is our claim. Further, next we shall show that next we have to show that any other solution of congruent 1 is congruent to any other solution except these, other than these, is congruent to one of these, one of the solutions in 3. So this we have to show, and for that purpose we shall consider a solution in general form, that is let x plus x naught plus n by d times t is any other solution. Let x naught plus n by d into t is any other solution. Any other solution of 1, the congruence 1. And now we apply the division algorithm for this number d and t. So applying division algorithm, for t and d, we divide t by d and let the quotient be q and remainder be r. And what is the condition for remainder? 0 is less than or equal to r, is less than d, or at the most less than or equal to d minus 1. It is integer, so less than d means equal to d minus 1. So this is the relation. And now we shall consider again this solution, x naught plus n by d. Now x naught plus n by d into t, this is equal to x naught plus n by d, and by division algorithm we have expressed t as qd plus r. So therefore we write it here qd plus r, or the left side is x naught plus, multiply inside the bracket. And now what this gives is n by d into qd, d cancels in the product and we get nq plus n by d into r. Check it. And now this is equal, we have written, now we write this is congruent. That means this number is congruent to x naught plus n by d into r under modulo n. Now you verify this. Why these two are congruent to each other? Because their difference, what is their difference? X naught cancels and this last term cancels n cube, and n divides n cube. So therefore these two are congruent to each other. And what is the meaning of this? This is any other solution, we assumed, is any other solution, and that any other solution is congruent to this solution. And what is this solution? This solution is one of the three. Why? Because R here, all the solutions are of the form x naught plus n by d into R, where R takes values 0 to d minus 1. Here it is 0, here it is 1, and here it is d minus 1. And therefore this shows that or we may write this value x naught plus n by d into R is one of the solutions in 3. This is one of the solutions in 3, and this is what we wanted to prove. There are exactly these d number of incongruent solution, and if any other solution we have assumed, then that is congruent to one of the solutions in 3. So this completes the proof of the theorem. So we may say this completes the proof. So the theorem stated the condition for existence of solution d must divide b, then the solution, then and only then the solution exists. And second, if the solution exists, how many d incongruent solutions. So remaining part we will continue next time. Thank you.